Any questions about logistics first? Okay. So, I think there's some broad themes of the course, right? So one broad themes of the course is kind of lecture 1, 2, 3. Do you understand multi-core architecture? And you better believe that we're going to ask you something about, do you understand that? So that's a topic we can go over today. Another major theme is just general tactics for optimizing parallel programs. Now, most of that stuff is stuff that you kind of get in your programming assignment, and it's just sort of like, you just kind of figure it out. So in general, like when students come into my office hours, we don't spend as much time on that before the exam. I'm like, if I give you a program and it has workload imbalance, like try and identify it. The other set of optimizations typically are you have a program that might have very bad cache performance. Can you improve the order of some loops or something like that to improve the cache performance? Then we talked a little bit about, what else did we talk about? So we talked about GPU architecture, which first of all you should think of as just like everything from the first 3 lectures, just you had it again, and it's no surprise that GPUs work the same way. I'd like you to understand the basics of the CUDA programming model in that there's an organization into thread blocks. There are threads in those thread blocks, but it's something you're presumably well acquainted with after the 3rd programming assignment. We had a lecture on deep neural networks. Now, the specifics of any deep neural network are not anything that you need to care about. But what was like maybe the 2 or 3 main concepts from the deep neural networks lecture? One was cache locality really matters. So we talked about blocking. And the other stuff was kind of all specialized hardware and things like that. We'll spend more time on that in the course, so I think that's more of a finals topic than anything else. We talked about data parallel thinking, so there's the possibility, it's fair game for me to ask you to go through a data parallel thinking exercise, that reinforces, were you the one on your programming team that actually did find repeats, or did you delegate that to your partner and now it shows? So, and then we talked about, the last lecture I gave was fine-grained locking. And we talked about compare and swap and implementing some locks. We talked about the relationship of that to how cache coherence works. Some interesting relationship. And we talked about using locks in like a fine-grained locking setting, and I've given you some practice problems on that. I can tell you that at the midterm level, the fine-grained locking practice problems will be simpler. Like probably nothing more sophisticated if I give you one on maybe a linked list or something like that. But you see some practice problems on hash tables and graphs and trees and other stuff. I'd like you to have a little bit more time to wrestle with that before I think it's reasonable for me to ask you a tough question. So in light of that, and then of course Kunle definitely talked about the MSI protocol and what cache coherence means and the main ideas behind that. And we talked about the idea of relaxed memory consistency, which is even though a thread might write X and then read Y, other processors might see those writes or reads in different orders, and there's some interesting implications of that. Cool. So in light of that, I'm happy to go over anything. And so I think those that raise their hand and vote with vote quickly will get more topics of their coverage. Otherwise, I can start making some topics up, but that may not be well. So, sir, you were the first to raise your hand.
I think last lecture we briefly touched on block-free programming. I was wondering if you just kind of go over some of the slides we might get to.
Sure. Yeah. Obviously, anything that we did not stress in class, I'm not going to bang you with.
Okay.
Yeah. Okay. So we talked about this idea of compare and swap. This is something I would like you to know. So up until this point in the class, we basically did all of our synchronization in 2 ways. We said that there were locks. And what does a lock ensure? Or in other words, what does mutual exclusion mean? Question for the class. Yeah.
One part of the code is only run by one thread at a time.
And this is a really important detail. Mutual exclusion means, as was just said, that only one thread, one actor, one worker, whatever, is allowed in a particular section of code at one time. which means that if I'm in that section of code, all of you are prevented from running it. Okay? And an atomic operation is basically of that mentality, right? Because an atomic operation is usually used on a read, modify, write. And it says that if I am reading and modifying this variable, nobody else is reading and modifying this variable. Okay? And compare and swap is one form of an atomic operation. It says, it's a read, modify, or really read, compare, write. It says, I'm going to read the value of this variable, and if it has a particular value, if it has, in this case, the value given by the argument compare, I'm going to write this new value to that position. Otherwise, I'm essentially going to write the old value to the position and leave it unchanged. That's an atomic operation. It's all whatever hardware platform you are running on. If you call compare and swap, it will guarantee that that is run atomically. That's what you can take as a given. And then I asked, we talked about, given atomic compare and swap, how can we implement an atomic min operation? So one way we could think about the atomic min operation as the hardware just gives me a new primitive, atomic min, and it ensures mutual exclusion because it's atomic. It's like if I'm doing a min on this variable, it's going to make sure that no other threads or cores can read or write to it. But look how I implement, that's a little bit, that's not how we design systems. We don't build a bunch of new primitives for every single thing that we want to do. We like to have one primitive that's rock solid and maybe fast and use it in a variety of contexts. So look at this atomic min operation and let's go over the philosophy of what happens. So what does min require? Min requires me reading the value from memory, checking if the value from memory is less than the new value that I'm trying to min with it. And if my value is smaller, we need to update the value of memory into something smaller, right? And that all has to be atomic. Now, first of all, I want you to make sure you can confirm to yourself that if you could do this easily without compare and swap if I gave you a lock. You would take the lock, you would read the value, you would check to see if it was smaller, you would potentially update the value, and then you would unlock. And that would be absolutely correct. And it would ensure mutual exclusion. Only one thread is trying to do the atomic min at once. So look, can someone describe to me what this code is doing? It's not ensuring mutual exclusion on the entire min operation. It's definitely not true. Different threads can have read that value from memory and be checking if their value is less than it at the same time.
I think if you look at the predicate upon which the min conclusion was reached, it's ensuring that that predicate is still valid when it writes that conclusion.
Right, so the idea is saying if I read the value from memory, then I start doing whatever work I need to do. In this case, it's computing the min of something. But maybe it was like atomic test primality or something, or that probably wouldn't work because I'd return a bool, but anyways. But let's say it's a more expensive operation, then I have to atomically perform some math, and then I write the value back to... I do my work. In this case, I do the work which is to take the min of the old value and the value that I have. And then I go back and I say, all right, if the value in memory is still the value that it was when I got started, I can be assured that no one else has come in. Or if they've come in, they at least haven't updated the min value. Okay? And that's what the atomic cast does. It says, if the value in this address is still the same as old, please update it to new. And I know if that is true because atomic cast returns old. And so I check to see if the old, if it's still, it returns the value in memory. And if that's old, that's the check. Okay. So let's think about this. Like, will that atomic compare and swap succeed if while I was trying to do my atomic min, you as another thread came in, read the value, checked it, and decided that you didn't need to update it because your value was too large? My atomic min succeeds. So what happened here is there's no mutual exclusion. We're both running at the same time in so-called this important synchronized section. But unless both of our actions create a situation where synchronization is needed, we can proceed. In other words, we are speculating, we're hoping that we're not going to conflict, and we're just going to go ahead. And then at the last second, before I do my write, I'm going to go check to see if that assumption was true. And if it's true, all the work I did is great, and I move on. If it's false, what's the cost of this? I have to do it again, and all the work that I did on that old value is potentially wasted. So what if this function was not min, but was something really expensive, like, compute some exponent on that value and then store the exponent value backward? Then I've done work, and I just got to throw it out, essentially. I essentially, every time I go through this while loop, I throw out my min work that I did, and I do it again. So this lock-free thinking is more like, hey, I need to make sure that I give the appearance that I get the same results as mutual exclusion, but I'm actually not enforcing mutual exclusion. And that's the big mental difference. And so what you're going to see after Thanksgiving is actually Kunle is going to give a bunch of lectures, and 2 of them are actually going to be about the idea of transactional memory, which kind of extends this idea to an arbitrary function writing to many variables. So you just write your function, it may read and write a bunch of variables, and the system figures out if any of those reads and writes conflict with another processor's reads and writes, and will actually abort and back one of the processors out. Okay. That's the level that I'd like you to know lock-free for tomorrow's assessment. And later in the lecture, if you're interested, I show you how to implement lock-free stacks and stuff like that. Like a lock-free linked list is given in some parallel computing classes. It would be complicated enough to get right that it would take me the entire lecture. It would only be insert and delete on a lock-free linked list. So I would not ask you how to do a lock-free insertion and deletion on an exam, for example, because it's actually incredibly tricky to get right. I'm not sure if I could do it off the top of my head on an exam. Yeah.
Could you say that lock-free programming leads to maybe a higher risk of starvation?
Well, there's nothing in this implementation. So first of all, what's the idea of starvation? Starvation is that the system is making progress. Some thread's making progress, but for whatever reason, one thread does not. Like the one thread never succeeds here, right? And there's nothing in this provision, in this implementation, to ensure fairness amongst the threads. But if you just had atomic lock and unlock implemented like we did last time, with the exception of that ticket lock example, there's also no provision of fairness. So lock-free versus mutual exclusion is not really, it's orthogonal from fairness. I could do something here which says after I've iterated through this loop, if I fail, maybe I should sleep, or something like that. I could do like an exponential backoff here, just like I could do an exponential backoff in a lock. Okay. Actually, did I miss anybody? Yeah, go ahead. Okay.
Is there any extra overhead that's caused when you call atomic casts, regardless of whether?
Well, let's talk about it. What is the overhead of atomic casts? So first of all, let's think about it in terms of a cache coherence protocol. So first of all, actually, how would you implement atomic cache if you didn't have cache coherence?
You would have to read from memory each time.
But it's atomic. How do you even implement? It's not just a read, it's a read and a write. You'd have to have some special provision in your system that kind of could say this is a current atomic operation on this address, and so no other core can access this address. Right? You basically build like a simple version of cache coherence for like a single address or something like that. So, but if you did have cache coherence, what is the cost of a cache? It's certainly a bus read X, so it's a write. Even if it fails, it's got to be a write, and that's expensive, right? And it's also basically it would be and it's not just a bus read X. It's a bus read X that you read the value, And then the cache coherence protocol cannot let that line be ripped away by another processor until this comparison and potential write has happened. In the same way that the cache coherence protocol, if you call bus read X puts the data in your cache line, and it's also kind of assumed that that processor is actually going to execute its write before it gets ripped away. Because if you didn't guarantee that, you might get into a live lock situation of two processors are just constantly bus read X, and then the line gets ripped away before they actually do the write, and so they're both sitting there on the same instruction just continuously. So you should think about it as once I get the line in the writable state, here there needs to be a comparison with another value and a write. So the cache logic has to, the processor just has to be a little bit more complex for that. Cool. Okay. New topic? Any other questions? Well, here, let's go here and then here. Yeah.
Sorry for doing back into the complete tunnel wondering if you could go over like MapReduce from distributed data parallel.
Sure. Yeah, absolutely. Let's see. Let me cut this off. And what specific is the question?
So I was looking at the run MapReduce like implementation, the job with like a bunch of diagrams and you have the key values and how they're.
And then you're talking about MapReduce itself, right?
Correct. Yeah.
So it kind of looked a little bit like this.
Yeah.
Let me just throw everything out. Okay. So in all of these programming systems, the first thing to think about is, kind of what is my API and what is the meaning of the API functions. And in MapReduce, there actually is only two. So the history of this, and I won't spend too much time on the history, is MapReduce was a very simple paper that came out of Google, and I can't remember what it was. It was probably like the early 2000s. This was before Spark, before a lot of... And the Google folks were saying that there's a lot of jobs that have to run at Google on an insane amount of data. And they was like, well, to handle an insane amount of data, like our entire index of the web, we've actually built Bigtable. We've actually built this shared file system. Right, so you basically, all the data in the world is in this file system, and the file system is distributed across a ton of computers. And they basically had a bunch of applications, like you can just imagine if you're like DevOps or something, you have a bunch of applications that are kind of data mining stuff on this big database. So the canonical example here would be like mining through a bunch of web logs or something like that. Like, so imagine you just had a huge file, terabytes of text, and every line in the file was like a log from Apache. Excuse me. Okay, so there's two function calls, right? The first function call was called map, and it was called map because it was inspired by data parallel map. And the second function call was called reduce, which was inspired by reduce, but they're very different than a little bit different than the definitions that I gave you in the data parallel thinking lecture. Map is the following. Let's say we're going to map, in this case it was, we're going to iterate over all lines of all files. Imagine you have this just gigantic terabyte file with a ton of lines in it, and different pieces of that file were just spread across different machines. And so before, like if you were a programmer at Google, you had to like somehow like get the data from the machine, bring it in, and do a bunch of stuff, right? Like it was just complicated because your files were spread out all over the machine. So map just says for every line in the file in this case, or for everything, I want you to run this function f, just like map. Okay. Now in MapReduce specifically, the output of map, if the input is like a line of the file, the output is not just like some arbitrary type t, but is actually a key value pair. Okay, so in this case, if I remember the example correctly, the input was a string, a line in the file, and then the f, the function that was mapped onto all the lines of the file, for every line in every file basically produced a key value pair. And in this case, the key was like the user agent, the browser, and the value in this case was actually just the number 1. But you could actually imagine like the key value pairs were like browser error message or something like that. So you produce keys and values. And then there's some magic that happens. And this is where, MapReduce was really clever in that so much simplicity was able to work for a lot of things, or really janky in that this is very hard coded. is that the system then takes all of those key value pairs. Now keep in mind that that map function can run across all of the machines. If your file is distributed across 1,000 machines, well, it'll just run that map function on the lines of the file on the machine that already holds the file, so the data doesn't move. And now comes the big data communication part. Every invocation of f produces a key and a value. And then what MapReduce says is hard-coded by design in the API, we're going to organize all of the tuples that have the same key into a file. So I have different files now for all of the different keys. And that file is just a list of all the values that match that key. So that's where the data just moved everywhere. It's like a big resort. In Spark, this would be called group by key or shuffle. Yeah. So map produces keys and values, and they get shuffled all together and they're reorganized. Here's all the data for this key. Here's all the data for that key. Here's all the data for that key. And because they had a shared file system, they already had it built, they actually stored this information in files. And so your parallel file system was exactly the transport mechanism to get all this data shuffling around. Okay, then you have reduce. And reduce takes as arguments the key and a list of values and produces a result. So the reduce function is actually mapped onto all of the unique keys. So the reduce function gets as input the key that it's working on, plus the list of values that were associated with that key, essentially the contents of a file. And now at this point, it does whatever the heck it wants and produces a result. And presumably it was called reduce because in this case, it takes all of those values with the same key, and in this case, just aggregated the number of lines with that key and returned the result. So the name reduce is actually not parallel reduce or anything like that. It's actually map group by key, map from a map where every element of the map gets a list and returns it to a value. So that, like in modern parallel programming, that's what it is. And so if you're like, that's pretty weird, I had all these computers, my data was distributed amongst all the computers, really our way of communicating would be to write to the file system and then read it back in from another node. That's what Spark said, that's stupid. And said, oh, we should just like do all this in memory. And that was the whole idea behind Spark. And do it with a proper set of data parallel operators, not just map, reduce, and group by key. Yeah?
Can you touch on that a little bit more, like why MapReduce required disk access?
This was how it was implemented. Like the only thing you can write in MapReduce is map to produce a bunch of key values. Then the system does a group by key for you. You have no question about that. And then you run another map, which is actually called the reducer function, which is map the reducer function onto all unique keys to produce one output per key. So the reducer function for a given key takes all of the values with that key and reduces it to something. But that's mapped over all keys. Yeah.
I'm not sure about this. I think like one reason why they were using like these concepts for the original MapReduce is because like commercial hardware disk was really cheap at the time. It's like at the beginning they don't really care about like the latency because the amount of data is not that huge compared to right now. Like for example, in the original Google file system implementation, like there's no replication for the master server. It's like a single point of failure. Like at the beginning, it's just.
Okay, so the comment here was about some of the motivations of MapReduce, and I wasn't there, so I can't speak authoritatively at all about it. But there was comments about, like the disk latency wasn't so bad. But first of all, that gives me a teaching opportunity. Let's first think about this as, am I worried about going to disk because of latency? I'm not worried about disk latency at all. Why am I not worried about disk latency? Why am I a heck of a lot more worried about disk bandwidth? I care about throughput, but latency can impact throughput, right? Like if I do one operation and then wait for a long time and then do the next operation, latency can definitely impact throughput. In this case, I'm only worried about throughput, though.
I
If you have a ton of nodes and they're all trying to write back to this, it's like that's a huge bottleneck.
Right, but first of all, that's why definitely I care about bandwidth. But I guess one thing I want to stress here is why do I not care about latency?
Can you just hide all?
This is massively parallel, right? There's billions of lines in a file. If I have to write a key value pair out, I send the write out and I go start working on something else. Or in the reduce phase, if I'm reducing over all the different keys, I start loading the data for the next key now while I'm working on this key. So all of our ideas of multi-threading, whenever you have massive parallelism, latency can be hidden. You care about bandwidth and throughput. So the real problem is that in between these phases of computation, the entire data set, terabytes of data, is read from disk and put back on disk and then read back in. Right? And that's true even if like the group by key doesn't really do much at all, like it's all narrow dependencies. And so people at the time were like, wow, I can write code in like 10 lines of code that use 1,000 machines. Like there's no, like I get fault tolerance, I get this parallelism, it's all handled in those two abstractions. And some of the folks that did Spark, and there's this paper that I have in my lecture slides about, or in Kunle's lecture slides now, I guess, about this paper that somebody wrote that said, yeah, but the applications that you're, like people were like, oh, we can do everything in Spark and MapReduce because it's so parallel and so awesome, but so low bandwidth. And then some folks popped open a laptop and said, you're using 5,000 nodes in a Spark or MapReduce cluster to process a data set that's like 500 gigabytes or something like that. 500 gigabytes fits in memory in my laptop. And they showed that one core of a laptop could outperform a 5,000 node Spark cluster just because people were getting enamored with parallelism and forgetting about locality and bandwidth. Right. Mm-hmm.
What kind of laptop is 500 gigabytes?
Okay, fine. I think the actual experiment was it was a laptop actually. I could go bring it up. I'll send it. Is they streamed it. So they streamed it off disk and showed that instead of going back out to disk every time, just keep a chunk in memory and then do 5 iterations, and then you can keep up with the Spark cluster. Another version of it would be these days in 2023, it would be for $3 an hour, I can go get a machine on AWS with 512 gigabytes of memory. And most of us, most of the time, are not working on problems that are exceeding what you can buy for pennies. And so it makes a lot more sense to think about locality, embrace that, and maybe scale to 4 terabyte size machines instead of trying to make your code robust to fault tolerance and failure on 10,000 nodes in the cluster. There's a great article by Amazon Web Streaming, the video folks, like Prime Video, so some of you may have heard of like Amazon Lambdas. So Amazon Lambdas is like you just give them a function and say, hey, like whenever I need to run this function, I'll let you know and run it for me. I don't want to think about servers and stuff like that. So the idea is to do like a computation like in maybe a second or so less. It's great because if like I have a website and I want it to always be running and nobody ever comes, I don't pay a dime if nobody's coming. And if people burst, it's really great because like they'll just execute all of those parallel functions for all these requests and I don't have to worry about scaling, even though the cost of those functions is actually quite high. Okay, so Prime Video built their whole system out of these microservices and lambdas. Like it was like, here's a little chunk of video, go do it with a lambda and stuff like that. And this is Amazon who's trying to sell the lambda service. And their Prime Video team has this great blog post from like a year and a half ago which says we built our whole system on Amazon Lambda, scale out massively. And now we've returned it back to a few small servers because of locality and other things. And so they said they're 10 times more cost efficient with a small number of big servers than they are with thousands of tiny servers because communication just bites you over and over and over in any system. Yeah.
Do they still get the same level of performance? Like is that like the given?
Yeah, like ISO performance 10x lower cost. And that's similar to some of these observations with Spark. So these systems that are scale out, there's one reason why you always want to, you want to think about scaling out if you believe that the data sets you're going to work on are going to be so big that you have no chance of keeping them in memory anytime soon. That's the reason why these systems are super valuable, right? Like if I have a database of terabytes and terabytes of data, I have no hope of ever keeping that in one node, so I should build fundamentally from day one in terms of this data can't fit anywhere, let's scale out. Okay, but I do want to get this back on topic. So let's move to another question.
Just a quick question on the default MSI without like.
Yeah. Let's actually do a cache coherence one. I think that would be a good. I actually did it in my lock-free lecture recently, so let's just pull up those slides. So we started the lock-free lecture in terms of this MSI protocol. Let me go ahead and pop it up. Now, on the exam, well, first of all, it's open notes. And second of all, if we've ever asked you to do anything with the MSI protocol, I've given you this diagram on the exam. So memorizing the diagram, probably not necessary. But in general, like, it's hard for you to answer a question without that diagram fully in your head. So they're kind of the same, right? Like if you're learning the state transitions off the, so should we just go over it or? Okay. Okay.
We were saying how it's like a bus read X, but I thought like if you do a reading followed by a write, just the default MSI has to do the bus read and then the bus read X. Is that incorrect?
That is incorrect. So let's just say I have let me make sure. I believe it's incorrect. So let's just say we have an address that is not in my cache. So if it's not in my cache, that address is conceptually in what state? It's invalid. Now, keep in mind, like I have a cache, and every line in the cache says this is the current address. So it's not like the cache has, a bit for invalid on all possible addresses. It's just if it's not in the cache, it's invalid. So then I do a read. And if I do a read, I will read it into the shared state. Correct? And then let's say I want to write to it. If nobody else has read it, it can be in the modified state now. Okay, so what is the question?
The question was like, that seems like a two-stage process.
That is a two-stage process.
So for atomic cache, since we're reading and then writing, is it that two-stage process?
Absolutely not. That's why I'm saying it's a write bus transaction, right? Because think of what can happen here. Let's say we don't implement cache atomically. The processor will elevate to the shared state. If it's not atomic, some other processor can now do whatever it wants, which it might generate bus traffic, it might write to the value, it might read from the value, and it will do its thing. And then when I do the write, perhaps it's still in shared or not, and it will then get elevated. So that's why the nature of cache or test and set or any of these things being atomic means you need to think about them from the performance protocol as a write, irregardless of whether the variable is actually updated by the transaction, right? So if I want to cast a variable, it's going to go from I all the way to M right at once. Mm-hmm. Otherwise, I would need special other logic to ensure the atomicity of that operation. In light of MSI, this is something we did last time. Would you like to go through a sequence? No? Or are there any higher priority items? I see some yeses. Yes? Okay, seems to be general. Okay, so this is the same sequence as last time. I mean, I think we didn't even do the whole thing last time. Let's go ahead and just do it. Okay? And I think this actually makes sense if we have, I just physically feeling it, is if someone wants to come up here and be the other, or if we have two caches, it can be very helpful. So let's just do it. Yeah, have somebody else, come here. I need two folks. If you're sleeping and you need some energy, it's like the first day of class. So you're going to be cache 1. Okay. Nice. And I need cache, I can be cache 2, or somebody else can be cache 2. Huh, we got cache 2, why not? Okay, so here we go. And this is what I want to, nice. You got to be above 6 feet tall to be a cache in this class. That's why I'm not volunteering. Okay, so here's the sequence, which you can look at it. So let's say that, just to keep you guys in the same seat, so let's have you be 0 and you be 1. I'm forgetting names, sorry. So we have cache 0 and cache 1. And let's get started here. And what I want you to communicate like the protocol. And then you can write on the board like the state that your line is in, right? So you can write on the board something like, I have X in the shared state. Okay? So at the moment, nobody has anything in their cache, so you have nothing. Okay, and then so let's just say the first thing happens is you say you want to load.
Okay, I have it in the shared state.
Well, not yet. Not yet. You actually have to say, I want to load.
Oh, okay. I want to load. Okay.
And now you have to acknowledge. And once you get the acknowledgement, you're like, oh, that's cool. I know that nobody's writing to it, so now I can put it in the shared state. So let's go ahead and write X in shared there. All right. So we got that acknowledgement. And then again, you load X. So what do?
Nothing.
You don't have to do anything, right? And that's an important detail. There's not even a message that has to be sent. Why does a message not need to be sent?
We have it shared.
By the nature of cache 0 having it in a shared state, we are guaranteed that everybody else might have it in the shared state, but they certainly don't have it in the modified state, and it's okay to continue to read. So nothing changes, and we're good. Okay, so now you need to write.
Yeah. But I want to write.
Okay, I see that. I still do nothing, right?
Yeah, so you're going to do nothing. And why do you shrug this off?
That's not even my cache.
You don't even have it in the cache. You can be like, look, do whatever the heck you want. Like, I'm not doing anything. So what are you going to do in your cache now? We're going to move from the S to the M state. Okay, and that M state means now that cache 0 is guaranteed that no other cache has the value. So you can proceed with your write. And in this case, actually, let's go ahead and write the value. You just updated the value. So it's X in M and has the value 1. And so if I'm like the third party, the under 6-foot memory system, like there's a value of X and Y out here in memory. And what's the value of X? It's actually still 0. It's stale. Okay, now let's keep going. So processor 0. Okay, so you're being greedy. You're going to write again. And you're going to update the value to 2. Which again, no coherence traffic needs to happen because we're guaranteed that cache 1 does not have the data and there's no business telling somebody something that they don't need to know. Value is 2, right? Cool, okay. Now, processor 1, now you're going to read it. Did I get that right?
No, processor 1 is me.
Oh, sorry, yeah. You're storing. Okay, so now some interesting stuff has to happen.
Okay, I need that because I need to write to it. So we can do this quicker.
Yeah. So hold on, let's sequence this very precisely. You correctly said, hey, I need to read. How do you react?
I say I've written to it.
Oh, so you have to flush memory.
Yeah, so you've got to flush. So in some sense, you send the value back to me. And I update this with the value 2. Right? You can, and then what do you do about your cache line?
And then, yeah.
Okay, and it's invalid. And now you have the value of this cache line, which you read from memory, and it has the value 2, and then you update its value to 3. You see that whole sequence? Now, if those of you are wondering why did this have to go back to memory and then all the way back, why not just like sort of transfer the cache line from one cache to the other? Any modern system has this. So you studied MSI, you studied MESI, and let's talk about that for a second. Intel, AMD, modern cache coherent systems are actually 5-stage systems. And that 5th stage is a special shared state, which basically says, if someone else needs the line and I have it, I will provide it to them without them having to go get it from memory. So it's just an obvious optimization that you're all wondering. But that optimization is not an MSI. Okay, where are we now?
I think I just read it, so nothing.
So yeah, so your next one is you just read, and that's like we're good.
Yeah.
And now, processor 0 wants to load.
Yeah, so I gotta tell you to write it, flush it to memory.
Yeah, so first of all, you go, I got it, hold on.
Yeah.
We got to do a flush. We flush to 3. And now,
And then I set this to invalid. Maybe use a marker.
okay, so this is an interesting detail. So you went to invalid. Now, first of all, here's a question. This is not the MSI protocol what you executed. But is it correct? As in, like, is it correct cache coherence? It's absolutely correct cache coherence.
Oh, this should be shared, right?
Well, I want to make it clear that what you did is correct in that cache coherence is still working. There's just an inefficiency. And the inefficiency is you could have kept it in your shared state. Keep in mind that the fact that processor 1 is invalid, this being in the shared state's okay. Because all this guarantees is that cache 0 can't write to the value. Right? So it was correct, just not a correct application of the MSI protocol. So yes, if you were following MSI, you would have said, I'm going to keep this around in shared state because there's no reason for me to drop it, and I might read from it again. And if I read from it again, it'd be great not to have to go get it from memory. Right, so now we're in a nice shared state, okay? And now it might get a little repetitive, but let's go ahead and do it anyways. So we have store, so you are storing.
I need exclusive access.
Okay. Well, I think you had it, but yeah.
Did you have it?
Do you have it? Let's see. Let's look at your caches. So, and actually you remember you're doing all of this without ever seeing the other cache's data structures.
I'm just doing the bus.
How do you know that another cache may have it? With your own data structures, and I'm blocking everything.
I
Right?
guess.
Yeah.
Do I just
Look here.
Yeah, right. It's in shared.
It's in shared, so you have no guarantees on perhaps somebody has it, right? So that's how you know what you can and cannot do. But in this case, there's a store, so you have to hold on. Notify everybody first.
Yeah, I need to.
Okay.
Because now keep in mind, notice that, like, what happens if cache 1 updated that value and changed its state before notifying cache 1, right? Like, it may have proceeded with the write. Processor 1, if it doesn't know that it needs to tear down and invalidate, might continue with reads. And that read may be potentially out of date, right? So before you update that variable, you have to get exclusive access. To get exclusive access, you have to say, I intend to write. Everybody else playing, all the other caches playing the game go, ooh, okay, I got to get rid of this thing. Go ahead, and now you can perform your write. Good.
And then would he write that to memory now, or I guess?
Well, let's talk about it. So there's a difference between what the MSI protocol is and what would be correct to do, but potentially inefficient. So we didn't write to memory after the write last time. And we didn't do that because why are you guaranteed to get the updated value whenever you read in the future? Let's think about it. So what's the process for reading in the future? And in fact, actually, the next line is you reading, so let's just go ahead. The next line is processor 1 loads X. So you're reading. Memory is out of date with 3. You have the invalid cache line.
So then that would trigger the flush.
Correct. So you state your intent to read.
Okay, I need to read.
You go, oop. And the memory, yeah, you're going to flush to me. The other thing we're not writing down is whether or not it's dirty. But I guess if it's in the M state, it's dirty. So was it 4?
Yeah.
Okay, yeah, 4. Now you can get 4. Yep. Mm-hmm. And we're good. Okay. Now there's one more detail here. This is the first time that it's a load of Y and not X. So both of you have X in the S state, and now there's a load of Y.
Yeah, I can just load Y.
But you have to say you have to load Y.
I'm gonna load Y.
Okay.
And you shrug it off.
Okay.
Yeah, and you shrug it off because you don't have Y. So just keep in mind that coherence is actually about that diagram, or that MSI diagram is about keeping coherence between the same address, right? In some sense, there's another copy of this diagram, another state machine rolling around for any other address, because there might be multiple values in cache. In this case, like you're keeping Y in S and X in S. And then finally, when processor 1 goes to write Y,
I need to modify Y.
modify Y, you shrug it off because you don't care. And then if you ever write Y, now you're gonna have to request it. There'll be a tear down, there'll be a flush of 1, and then so on and so on. Exactly. Okay, this is the whole, so it's very important to think about of any change in state to my local cache will result in shouting to all the other caches. Because the data structures of the other caches have state in them that allows those caches to make decisions about what they can and cannot do. And if my state changes, I gotta tell everybody else. How we tell everybody else is not something we talk about in this class. We talk about it as shouting as if it's a broadcast, but typically under the hood it'll be point-to-point messages and stuff like that. And that's a different detail for another class. All right, thank you very much for your demonstration. But any other questions on cache coherence? Yes?
One cache has the data in modified state.
Okay, one cache has the data in the modified state. Okay.
Another cache wants to read or write to it. Like, do we have to send the data back to memory? We can't see cache which has the data in the modified state.
So let's say that cache 0 has the data in the modified state. Cache 1 wants to write to it. And what's the question?
Like, why does the data need to come from the memory? Like, why does the first processor need to flush the data back to memory, and then processor 1 gets it from memory rather than processor 0?
Is your question, why does processor 0 not give the data to processor 1? Well, that's what I was saying earlier. In a more complicated cache coherence protocol, 5-state protocol, it's called like MESIF or MOSI, there's a 5th state which says, if you're trying to get data from memory and another cache has an up-to-date copy of the data, that cache will provide the data. But I do want to be clear about one thing. Remember, we're talking about cache lines here, even though we kind of assumed in that exercise that the cache line size was 1 value. So when we say load X, we really mean the cache line containing X. So let's say X is here, and I write 4 to X. Keep in mind that there's data here in the rest of the cache line that is untouched. So the reason why I write it back out, the cache line all the way back out to memory, is that I need to update that whole cache line. Like, I can't just send 4 because I don't know what's dirty in this cache line at all. So just make sure, even though that demo was in terms of single values, the information that's being flushed or communicated in a more advanced protocol are entire cache lines. Okay. You would have to have a more advanced cache that was going to track dirtiness at the bit or at the byte level. Yeah.
So you just mentioned in Intel CPUs that there's actually a diffuse state which allows cache transfer from one core to another core. Does that take care of this situation?
What that does is avoids the flush. It avoids the flush. So if I'm a cache and I have the line in the shared state that you need, if you read it, I'll just give you the line and now we both have it shared. If I have a line in the modified state and you need it to read, I will give it to you and flush it to memory and we'll both be shared. Right? If I have it in the modified state and you want it in the modified state, I can actually just give it to you without flushing and you have it in the modified state. And now you're responsible for flushing it. Yeah. Mm-hmm. Yep. So that's more advanced details that we don't. Okay. So what about this messy, this 4-stage protocol? This might be a good check your understanding. Do we have, I don't know if I have Kunle's slides, so hold on one second. So in MESI, you still have the same modified, shared, and invalid states as before, but there's this little exclusive state. Did we talk about what that? Yeah, we did, right? And what's the advantage of this 4th state? And let's think about a particular use case where you read a value and then at some point later you write to it. Very common case in computer science. Yeah. Correct. So let's think about MSI in the case where a thread reads and then writes. If a thread reads, I bring it in as a shared state. All I know at this point is that there may be other processors with the data. So if I go to write to it, I also have to speak up and say, hey, I'm going to write now. Okay? MESI says when you load data, when I say, hey, I want to load the data, you look at what the other person says. And you say, if the other person says, oh, yeah, I've got that in the shared state, you go, okay, I should have it in the shared state too, because I know that it's possible for other people to have the data. If nobody says I have it in the shared state, if everybody goes, I don't care, why are you telling me? I can load it in the E state, which says that it's not dirty, I haven't written to it, but I'm guaranteed that nobody else has it. And so if I ever want to write to it without telling anybody, I can just flip from E to M. Because nobody else has it, so nobody cares about what I have to say about that line. Yeah.
What if someone else thinks it at the same time? Like, should you have something that shifts it from E to S?
So if I have it in the exclusive state, and, well, I haven't finished the diagram, sorry. If I have it in the exclusive state and I hear someone else's read, what do? I drop to shared, and hope that should be on the diagram now. I still haven't finished the diagram, sorry. Okay, so if I'm in the exclusive state and I see a bus read, I don't do anything and I drop to S. Go.
So like after the cache is running a value, can you ever go back to the exclusive state, like if two caches have a value or shared, and then can you ever go back to the exclusive after another fossil kind of...
And you can see it from this diagram in that there is no transition, right? What it would take to do that, let's talk about it. Let's design a cache coherence protocol that's better. What would it take to be able to elevate from S to E?
You'd have to tell all the processes to make it invalid.
You'd have to tell all the other processors to go invalid. So you would have it in your shared state, and then every time you wrote to it, you'd have to tell all the other processors, hey, I'm writing again. You have it still? So that kind of almost defeats the value of the shared state. But what we could do is that whenever any processor went to invalid, normally when you go to invalid, it's in reaction to other things. Let's say you go to invalid because like you got evicted from your cache, not based on anybody else. You could tell everybody else, I'm going to invalid, and that could be a trigger for all the caches to report, do I have it in the shared state or not? And if only one cache had it in the shared state, then you would know you could elevate to E. Just be a more advanced cache coherence protocol. Yeah.
A question over here, when we loaded in Y at the end, we knew that X was not in modified state, but if
when we load in Y, X was already in a modified state, would we be required to first flush X?
This is a great question. I want to make sure everybody understands it. So the question was, we have X in some state. Let's say it's the modified state, the cache line X. If the cache line Y is loaded into the cache, does that change the behavior of X in any way? No. Right? Because they're different. Coherence is about a state machine for every address in the system. And different addresses do not interact. The only way they interact is nothing to do with parallelism, is maybe bringing cache line Y into the cache caused an eviction of cache line X. And then that would be something that caused X to invalidate, and then it would have to flush. But that's unrelated to the discussion of cache coherence. That's just a normal cache behavior. Right? Okay. All right.
If we have like an example where our cache is full and then we're going to do like some operation, is there like an implicit write back when we even do like a processor read or something like that?
Absolutely. Like let's say, and we could talk about normal cache behavior unrelated to coherence. So imagine that the cache and by the way, the cache is always full, but you read a new value, which means you're going to have to kick out an existing value. You decide which one to kick out using whatever policy, and if it is dirty, the process is write, okay, so if it's dirty, it's already in the modified state. So the process will be flush the data and go to invalid, and then bus read X on the new thing. Or sorry, bus read on the new thing.
And would that like be part of the with like
No, because the other line is some other address. And again, this is how we take this one address. So from the perspective of this cache coherence diagram, you just would not initiate the bus read X on address X. until all the appropriate room in the cache has been made to put X in your cache. So there would be some other diagram for state Y that would now be moving from modified or shared to invalid. Yes, okay.
So you mentioned that this state is maintained per address.
Per cache line. Yeah. Yeah. Okay, should we move on to a different topic or still? Yeah, let's move on unless you had one last follow-up. Okay, so maybe shout out some different topics because I think if we go an extended session, we can either get 2 more in or 1 more in. So let's aggregate. What are some topics? Segment and scan, okay. Data parallel thinking, anything else? CUDA in general, you might need to be more specific than that.
Yeah, just like how the warps, how these things are organized.
How are warps organized onto a machine, okay, and then?
Memory consistency and how to solve the problem.
No secret sauce. Just think about all. I mean, okay. So okay. Let me answer that one first because I don't think doing a problem will be the best. I think you're just doing it on your own will be best. Is one of the things in this class is very much a skill that we want you to have. Is think through what operation is running on a machine at what time. Like what's the schedule. So you're like, oh, like this thread is running this instruction on this core when this thread is running this instruction on this core. Okay. So there was a practice problem, if I remember correctly, this week, which was instruction interleavings. Right? So we said, let's say I just have a thread T0 that does instruction 1, 2, and 3. And I have another thread T1 that does 4, 5, and 6. Okay, so the only thing that's required is that T1 better do 1 before 2, better observe 1, then 2, then 3. And T1, maybe on a different processor or a different thread on the same core, has to do 4, then 5, then 6. If I put these into a timeline, there's nothing preventing, 1 coming before 4, 4 coming after 2, 3 happening in here, and so on and so on. We want you to be able to think through all the possibilities of what could happen and what the observed results would be. Okay, so what I just did there kind of assumes sequential consistency, right? Like there's like some total order that exists. When we go to relaxed consistency, what can happen is there is not a possible way to put all 6 operations just on a timeline when you say the effects of the program are consistent with this being the order. That's what relaxed consistency is. It's like, if this is a write and this is a write, well, this processor clearly has to do 1 before 2 because that's the program. But the values, those updates, might appear in different orders to somebody else. So that's the whole concept. There's not a lot of magic about it. And it's different from coherence. Because here we're talking about the order of the effects of 1 and the effects of 2. Operations to different addresses. Coherence is all about operations on the same address. So they are orthogonal concepts completely. Okay, so segmented scan and a little bit of just CUDA mapping. Yes?
You mentioned even for relaxed consistency, we follow the order of instructions. That's not always true, right? You can reorder reads and writes, for example, right?
Let me be very precise about this. If we have one thread of control, your compiler, your hardware is broken if you get results that are in the opposite order or that are not consistent with program order. So nothing about relaxed consistency can be visible if you only have one thread, right? In the same way that superscalar execution is broken. If a processor decides to execute instructions out of order or in parallel and you get different results.
So you're saying commits are in order either way in a single thread?
In a single thread. Yeah. Relaxed consistency is saying if T0 believes it sees write to X and then write to Y, if you read, if you read a value in here, you would see the X done and the Y not done. If you read a value here, you would see both of them done. What relaxed consistency says is that if T1 ever reads X and Y, it can observe, if you are relaxing right ordering, for example, T1 might see the value of y being updated before it sees the value of x being updated. Okay? And I want to be really clear that this is only something that when we're talking about the observation of another processor's writes, right? Because if we're talking about my own writes, and I compile a freaking program, and it gives me an answer that's not consistent with C semantics, I throw out the computer and the compiler and say this is all broken, right? Exactly. So I want to be very clear about that. And keep in mind that within a thread, on the first day of class, I told you that instructions were reordered. Superscalar does that, a bunch of reasons done that. But you never, ever observe that they are ordered. So it's still completely in program order.
So just kind of going on top of Steve's question, I would like to see if we can go over, like, just in general, all the possible parallel mechanism I'm covering the course so far. Like,
you just increased scope in the last 12 minutes here considerably. Wait, so what? What are you asking?
Like, so for example, what kind of
Put it this way, it's extremely hard to even create questions that do much more than right reordering. so they're done extremely hard. So I think right reordering is a big one. But basically, not even right reorder. Just think about if you have a write. Think about the implications of moving reads or other writes above or below it. Right, I think that's a good guidance. Like if we tell you, or it can be easy to just say everything is relaxed, like just no guarantees on anything other than program order. Yeah, but the easiest questions to write are definitely right reordering. Okay, so I see. Like this is the data parallel lecture. So there was a quick comment on segmented scan. All I want you to know on segmented scan, and you have it on the slide, is the definition. So segmented scan is just a scan. Imagine that we had a list of lists, or if I wanted to be more precise, a sequence of sequences. So here's a sequence of 2 sequences. The first sequence is 3 elements, and the second sequence is 5 elements, right? Imagine we did a scan on the first 3. The first sequence, what would we get? Let's say it's a sum, an exclusive sum. So if it's an exclusive sum, we would get 0, 1, 1 plus 2, 3, 3 plus 3, 6. And then, so we know what a scan is. Now imagine that now I just do a scan on the next thing. And I'd get, again, 0, 4, 9, 15, 22, 30. So I just 2 scans. So if you know scan, you know what the right answer should be for segmented scan. Now, segmented scan algorithm that I gave you on the page is a way to compute those 2 scans with O of n parallelism, where n is the total length of all the subsequences. And that algorithm looks a little bit like this. I visually described it like this. I put this in the lecture because I thought you might find it cool. What I want you to be able to do, however, is, yes, if I gave you the definition, if I gave you the bottom half of this slide, and I asked you to use segmented scan in some higher level algorithm development, that is fair game. But I won't be like, hey, you need to implement data parallel scan. Yeah. Or if I ask you to implement it, it's going to be some very guided thing where the real principle is something else and not the segmented scan. Okay, so that was that, and then CUDA. So let's try and let's see what we can do with CUDA. Okay, so I hope you all remember from assignment 3 that when you, and really from your assignment 2. So in assignment 2, we had these bulk tasks, right? So in some sense, you had a task system, and the application sent you a command, and the command was run this task n times. Right? And then it can send you multiple commands, which said, okay, here's a new task that you need to run n times, but you can't do any of these until you're done with all these previous bulk launches. So CUDA is a bulk launch system, much like your tasking API. It just kind of has, instead of the number n tasks, it just kind of has two numbers in there. It says, I want you to run n thread blocks, and each thread block has t threads in it. Okay, so it's the same bulk launch concept where you say, here's the number of thread blocks, and I think thread block and like kind of your task or an ISPC task have a bit of correspondence. And inside that task, you're going to do parallel work using t threads. So the fact that you can do this in 2D versus 3D versus 1D is not significant, right? It's just create this many thread blocks, and every thread block needs this many resources. It needs this much shared memory, and it needs this many threads. Okay? So in this setup, the details of the program are not important, but we wrote a CUDA program that, if I remember correctly, had 128 threads per block and needed, I can't remember, it needed like a little bit over I think it needed like it needed a little bit over 512 bytes of storage. So in other words, if we have on every core of the GPU, every SM of the GPU, if we have execution context for 384 threads, how many thread blocks can we fit? What? 128? Just, you do the math. Can we fit 2 or 3? I can't remember. We can fit 3. Yeah, we can fit 3 thread blocks worth of threads. And if those thread blocks needed a little bit over 1/3 of this shared memory, how many thread blocks can I fit from a storage perspective? Just 2. Right, so in this case, the number of thread blocks that we can get onto this processor at one time is actually limited by our shared memory. But for example, if it used 0 shared memory, I could fit 3. So I say that there's an execution context for 384 CUDA threads here. And so the NVIDIA scheduler, their version of your assignment 2, is going to say, all right, here's some work. I want you to run 1,000 thread blocks worth of this program. And at this point, it just starts handing it to its worker cores, right? And so, or really, it's worker execution context on its cores. And so step 1 is to say, well, look, there's nothing allocated right now. Let's get the first thread block running on core 0, and we're going to give it 128 threads worth of execution contexts. And we're going to give it a little bit over 1/3, 520 bytes of storage. And there's still a lot more worker capability in this machine. So we're going to assign the next thread block over here on core 1. We're going to assign, now question, a good exam question would be, why did this scheduler, which was an implementation detail, but why is it a fairly sane decision to put block 0 on core 0 and block 1 on core 1?
So both cores could work instead of...
If I would have put block 0 and block 1 both here, what is the performance implication of that? Because remember, these are 128 threads. These are 128 threads. We have one core, and that core, in this case, had a 32 wide SIMD capability. What's the problem with loading this up with a bunch of threads and leaving the other core idle? Yeah?
We just make it inherently sequential within that one core instead of utilizing...
Because remember, these threads are interleaved onto these processing resources. So I'm having everybody that I'm creating, telling to do work, share the same resources while I have resources over there that are idle. Exactly. Okay, so I have more room. I can fill up this chip, and this chip can simultaneously support 4 concurrent thread blocks. Okay, and I cannot put further thread blocks on here because I'm out of resources. So when a thread block completes, just like in your assignment, when a task completes, that opens up the ability to put another task on the machine. So let's say the first block completed first, which makes sense, and the scheduler can fill that gap. Notice that the fact that all thread blocks have the same number of resources and the same allocations is useful for filling this gap. Otherwise, you have an allocation problem. Okay? And we just continue with that, just putting stuff on until we're done. Okay? So that's the thread block scheduling part of CUDA. Is there any question about warp scheduling part of CUDA? Or are you good there?
So my original question was, why is it on a single core at a single clock, how many warps can we actually clock?
Okay, so, and I'm gonna, I want to preface this because this is recorded and I don't want to be doxed because I'm saying the wrong thing about modern NVIDIA GPUs. But for most NVIDIA GPUs, it's perfectly fine to think about it in the following way, is that the chip has a bank of ALUs. Now, this is not an NVIDIA GPU. I made this up. My proxy NVIDIA GPU here has 32 SIMD ALUs. And the way it runs CUDA threads is it takes 32 CUDA threads, which is called one warp, and it runs them one instruction for each of those 32 CUDA threads on this ALU and makes progress on the warp. And then the next clock, it might choose a different warp. So you can think about a warp's worth of execution as 32 CUDA threads all doing the same thing at the same time and concurrently running on the chip. Okay?
Does it always choose the threads or what's from the same thread block?
I'm going to answer the question was, does the NVIDIA GPU always choose threads from the warp in the same thread block? Officially, NVIDIA says nothing about their implementation, so I cannot definitively tell you, do they do that or not? Historically, the answer about their implementation has been absolutely yes. The threads that are used to run at the same time are thread IDs 0, 1, 2, 3 all the way to 32 mod, like thread ID mod 32, 0 through 31. Now, this might be a elite mode way to finish up here, but in the last minute, let's think about it this way. NVIDIA has full flexibility since you wrote things as threads. If they want to change the SIMD width and cut the number of ALUs by half, you would never know, right? Because you just created 128 threads. You didn't think about warps. You didn't think about any of that stuff. So when you compile your thread block code, it's just a regular sequential scalar thread, and it happens to run as many as you asked for concurrently. That's different from the implementation detail of SIMD instructions on a machine. If we went next year and Intel produced a processor with like 64 wide SIMD, you would go back to ISPC, you would change the gang size to 64, you would recompile your code, and it would produce one thread with 64 wide vector instructions. That's the one difference between GPU SIMD and CPU SIMD. In CPU SIMD, it's the responsibility of the compiler to generate instructions that are exposed by the machine architecture. In GPU assembly, the compiler doesn't do nearly as much. It just generates sequential things and says, like in your programming assignment, we're going to do thousands of them at once in block sizes of, in this case, 128. It's up to NVIDIA to decide how it wants to run that. Historically, it's taken all your threads in a thread block, chopped them into groups of consecutive 32 addresses, and run those in parallel. These days, they actually do have the ability to rearrange things for you in order to try and discover better SIMD coherence if you have diversions and if statements. The extent to which they can successfully do that is complete trade secret and not something that's well documented.